In this video, I want to have a look at the exponential function e to the power of x. So before we have a look specifically at that exponential function, I want to look at exponential functions more generally. So an exponential function has the form f of x equals a to the power of x, where a is a number. So for example, it might be 2 to the power of x, 10 to the power of x, it could be anything. Now all exponential functions in this form have a graph that looks something like this. So it starts close to 0 and it increases as x increases. Now if we were to graph the derivative function of that curve, we're looking at the gradient. So you can see that over here the gradient is close to 0, and as we move right, that curve gets steeper and steeper. So as we move across, the gradient starts at 0 or close to 0, and it's increasing as we move across. So if we were to sketch the gradient, it would look something like this. So over here, the gradient is close to 0, but it's still positive. And as x increases, that gradient is increasing as well. So what we end up with is the gradient curve looking incredibly similar to our original function. Let's have a look at a few more accurate graphs. Okay, so I've got GeoGebra open here, and what we've done is we've put a slider in that has values of a equals 2 at the moment, but it goes all the way up to 10. And we've got this function that's got a as the base. So like I said, a is 2 at the moment, so it's 2 to the power of x. So as we increase a, that's 2.5 to the power of x, 3 to the power of x, 3.5 to the power of x, and you can see that as the base number increases, the gradient of that curve increases as well. So the curve gets steeper and steeper, and as we come back towards 2, it flattens itself out. Now we want to have a look at the derivative of that. So that function there is f of x, but we're also going to graph the derivative, so f dash of x, and that's this blue one here. So the function 2 to the power of x, this is its gradient function or its derivative function, the blue one there. So it's not quite as steep. Now if we increase it to 2.5, you can see that the steepness increases, so it gets closer. Then we've got 3, 3.5, 4, all the way up. So you can see that they have a similar shape, but they're not exactly the same. But right here, between 2.5 and 3, it switches which side it's on. So that means that somewhere in between there, somewhere between 3 and 2.5, there's a number where the blue line is going to lie exactly on top of the red line. So that means that there's a number where the gradient function or the derivative is going to be exactly the same as the original function. And that's what we're going to have a look at today. Okay, so what we've just had a look at is that the derivative function of an exponential function will always have a similar shape to the original. So technically the derivative of an exponential function is always a multiple of the original function. Now we were looking to find when the derivative is exactly equal to the original function, and we knew that it was between 2.5 and 3. The number is actually an irrational number, similar to pi, so in that it goes on forever, so it's the same sort of number. It's called e, and it's an incredibly important number in mathematics. So e is approximately equal to 2.7, or 2.718281, but it is irrational, which means that decimal will go on forever with no pattern. So the exponential function f of x equals e to the x is its own derivative. So that means if we find the derivative of e to the power of x, our answer is just going to still be e to the power of x. So the one last thing is that geometrically, this rule means that because the function itself is equal to its derivative, it means that the gradient of the function at a particular point is equal to the height of the function above the x-axis at that point as well. Right, so that's an introduction to the function e to the power of x.